Hello everybody, I'm here with a problem where has three parts, where the first part I want to use work energy principle to solve the problem, solve for the speed. And then the second part B and the third part, part C, we're going to use the concept of F equal ma, or second law, to solve for forces and rate of change of speed. Okay, so let me tell you what's going on here. So we are given that, first of all, this color is 2 pounds, right? And actually at position A, when the color is here and the spring then would be like this, right? And I'm going to call this position 1 actually. Velocity at this instant is given to be 5 feet per second. We are going to neglect friction, and by the way, this is in a vertical plane, right? So gravity is going to be considered here. We are also told that the spring has an undeformed length of 2 feet. So obviously, based on that, we can figure out how much the spring is deformed. So the first thing we want to find at position 2, or when this the color is at B, right here, right here, we want to find the speed. So I'm going to call that calling this position 2. So we want to determine what is the speed here, right? V2. And the second part, which I'm going to go to the next page in a minute after I'm done with the first part, we're going to find the normal force and the rate of change of speed. Now, normal force, I'm going to call it N. And rate of change of speed is A sub t. Remember, A sub t is rate of change of speed. It's defined as dv dt or v dot. So in the second part, we want to find the normal force that the rod exerts on the color, and also find rate of change of speed. But remember, the first part is I'm going to use work energy principle. So what is work energy principle? The work energy principle, we're going to say that work is equal to change in kinetic energy right? And remember, symbolically, that would be U12. You've seen this in another example, hopefully. That would be KE2, kinetic energy 1 minus kinetic energy 2 minus kinetic energy 1, or changing kinetic energy, if you want to write it like this, delta KE. All right, if you put it in the symbolic form, you recall that we can have work, could be work of an external force, work of gravity, which we do have, work of a spring, which is calculated like that, and then work of friction, which again in general I put it as an integral, equal change in kinetic energy 1/2 mv2 squared minus 1/2 mv1 squared. Okay, so as you've seen in other examples, I'm going to go and figure out which work is going to apply to our case. There's no external force, there's no friction, but we do have gravity and we do have work of force of a spring. So therefore, we're going to figure out or rewrite our equation. First of all, the work of force of gravity, is that work is positive or negative? Now you see that the work is just W, the weight, times Y. Y is the vertical displacement. Since this guy starts at 1 and gets to position 2, it's moving down, or it's moving with gravity, the work is positive. If it was going from 1 was this position at B and it was moving up, it was going against gravity, the work would have been negative. And then the work of force of a spring, of course, is just this formula, right? And we're going to just plug in what's given. Just a reminder that in this case, S1 is how much the spring is deformed at position 1. That's 4.5. Look at the length of the spring here at this position. 4.5 minus the undeformed length 2, right? So S1 is 2.5, right? And S2 would be what? Look at the spring when the color is here at B, or position 2. We have 3 feet minus the undeformed length, 1 foot. So be very careful, guys, with that. The actual length minus the undeformed length will tell you how much the spring is undeformed. So let me go ahead. Be careful with the units, guys. 2 is the weight of the object. And what is y, by the way? From position 1 to position 2, the object moves vertically 4.5 feet, right? So that's a positive work. The work of spring is 1/2. K, remember, is 10 pounds per foot. S2, remember, is 1. And S1 is 2.5. Also on this side, be very careful. Mass is 2 divided by 32.2. V2 is velocity I'm looking for. And V1 is equal to 5 feet per second, right? That's given right here. So 2 divided by 32.2, 5 squared. So if you go ahead and calculate this, right, the velocity, I believe, becomes 34.1. So velocity as it passes or as it gets to position 2 or point B would be 34.1 rather, sorry, feet per second. So you'll see now in a minute when I go to the next page, this velocity is going to be used to calculate for parts B and C, which is normal force and the rate of change of speed. Okay, guys. So be very careful, guys. Now, it appears as if this guy is traveling, along like a circle, but it's not. The parabola, it's a parabola actually, and the profile of the parabola is given. And basically, this would be the tangential axis, and this would be the normal axis at this instant. And you'll see that in the next page. So we have to go ahead and find this angle, because we need that angle to be able to break, different forces like the weight or force of a spring into our tangential and normal direction. By the way, why are we using N and T? Because this is a curvilinear motion. The object is going along a curved path. So it is convenient for us to use N and T. So how do we find this angle? Remember, tangent of this angle, tangent to the path, which defines tangential axis, is actually equal to the first derivative. And remember, if you plug in the x value, which in this case is 3 feet, that's how you find the angle. Let's go to the next page. So I have done all the work here for you. So if I take the first derivative, which actually, remember the equation is what? 4.5 minus 1/2 x squared. Let me write that here for you. Y equal 4.5 minus 1/2 x squared. So if you go ahead and take the derivative of that y prime, that becomes minus x, right? If you plug in x equal 3, y x equal 3, because that's x equal 3, right? That becomes negative 3. Take the inverse tan of that and you get 71.57. That would be this angle. Negative just means, it's a negative slope. But the magnitude of this angle, theta, is 71.5, or a little bit more than 71.5. Now, what I did also, because we need to calculate normal acceleration, and normal acceleration is v squared over rho, I already have the velocity. Velocity is 34.1 at that instant, but I need to find rho. You guys recall in other videos that if you have the profile of the path, right, which is this guy, you could use this formula. So I went and I took the second derivative, which is negative 1. I plugged into the equation 1 plus y prime squared raised to power 3/2, so y prime is negative 3, square it, add 1 to it, raise it to power 3/2, right? Divided by absolute value of y double prime, I get a 31.623. So I came over here and I took velocity squared and divided by rho, and that gave me the normal acceleration. That's the number I need. So I drew the free body diagram here for you guys. Remember the t-axis that I defined here for you, right? That angle is important. Normal axis. And remember, along the normal axis, you have the center of curvature, and the radius of curvature we just determined. Based on that radius of curvature, we calculated the normal or centripetal acceleration. So our objective in the second part is to find the normal force. So I showed the normal force here in the yellow color here. We have the weight of the object, obviously, 2 pounds, and also the force of a spring. Don't forget that the spring has a force here. What is this force of a spring? Well, force of a spring is what? K times, and this is position 2, K times S2. What is S2? 1, right? Here we go. 3 minus 2, that's S2, 1 foot. So 10 pounds per foot over 1 foot, we get 10 pounds. So this force right now is 10 pounds, guys. So the rest is just resolving the forces in the normal and tangential direction. So I started with some of the forces in normal equal mass times normal acceleration. What forces we have in the normal direction? If this is our positive normal direction, normal force in our case is negative. By the way, we could select any direction we want. You could put the normal force this way or the other way, right? If you get a positive answer, your direction is right. If you get negative answer, you have to switch the direction. So in this case, I assumed n is like that, so I have a negative n here plus the component of the 10 pound along the normal axis is, you have to use the sine of 71 or sine of theta. The component of the 2 pound along the normal axis becomes 2 cosine. Equal mass, be careful, mass is W divided by G times this normal acceleration that I calculated here. So if you solve for n, n comes out to be positive, which means the direction of the n here is correct. And then, of course, so that's answer to part B. And then part C, sum of the forces in the tangential equal mass times tangential acceleration. So some forces now in this direction, right? T-axis, right? And basically, if you look at 2 pound, you use cosine here, right? You have to use sine here. And then the component of the force of a spring, the 10 pound, we use sine here, we have to use cosine. Just be careful with the directions. The contribution of the weight is positive, but the spring along the tangential axis would be negative. Equal mass times A sub t. A sub t is what we're looking for. A sub t is the rate of change of speed, dv dt, or v dot, right? So it turns out that the spring will overcome the gravity, so we end up getting a negative answer, which means the speed is decreasing at this rate. Speed is decreasing. If you get positive, that means increasing. Speed is decreasing at this rate. What rate? This rate of A sub t at 20.4 feet per second squared. Again, thank you for watching and listening. And as I said before, in other videos, if you like this video, please subscribe, and I'll have many more videos coming your way. Thank you again.